Large field of view video measurement. Important considerations. The use of video measuring microscopes and comparators is common in modern manufacturing. They are capable of performing fast, accurate, non-contact measurements. Traditional video measuring microscopes and comparators have some shared optical characteristics. They have a relatively small field of view. That is the area visible at any one time. On both traditional and large field of view systems, the size of the field of view is related to magnification in that the higher the magnification, the smaller the field of view. However, large field of view systems can provide a field of view 14 times larger than a traditional system. For instance, you may be able to view the entire 3-inch, 75mm part on a large field of view system while only seeing about 250 thousandths, 6.35 millimeters within the field of view of the traditional video measurement system. This small field of view often makes multiple stage moves necessary in order to measure the entire part. Consequently, fixturing is usually required to keep the part stable and ensure accurate measurements. Multiple moves in order to capture measurements over the entire part increase the inspection time required. The large field of view system's ability to visualize and measure more features in any given field of view location aids in decreasing the amount of time required to measure the part. The optics or lenses used to magnify the image in traditional video measuring microscopes and comparators have a small depth of focus. The depth of focus is the range of image plane position at which the image may be viewed without appearing out of focus for an object or specimen that does not move or change location during the viewing. This characteristic is very useful. Because the depth of focus is small, targeted features can be brought into sharp focus by analyzing the image as the optics are moved closer and farther away from the target to find the sharpest image, often referred to as autofocus. While this capability adds measurement in the axis of the optics, it is at the expense of time required to bring each targeted characteristic into accurate focus. When only XY plane measurements are required, a large depth of focus can speed inspection time significantly by not having to refocus on features not in the same plane relative to the optical axis. In this comparison, we are going to consider two more optical characteristics. They are telecentricity and distortion. Telecentricity is the optical characteristic that allows an object to appear to be the same size and shape regardless of its distance from the lens. This characteristic, coupled with a large depth of focus, is at the core of the capabilities of large FOV measuring microscopes and comparators. If the image is accurate throughout a large distance from the lens, the system does not need to refocus in order to make measurements on features not in the same plane. Distortion is the optical characteristic that allows an object to be accurately magnified, maintaining both size and shape throughout the field of view. This characteristic allows for measurements of features throughout the field of view, eliminating the need to move the part. The result is faster measurements by taking advantage of the much larger field of view. A simple test. This video shows a QVI snap measuring a standard calibration sphere that is commonly used to calibrate coordinate measuring machines. We use this artifact as it is traceable and reasonably common in the manufacturing world. The sphere is positioned on the stage in the center of the field of view at optimum focus and measured using the system's edge detection. Then the stage is moved 200 thousandths, 5 millimeters closer to the optics, in this case up in Z, and measured again. This is repeated in 200 thousandths, 5 millimeter increments throughout a total of 2 inches, 50 millimeters. The total range of measurements is noted. This number gives a good representation of the telecentricity of the system. The sphere is then repositioned on the stage at the edge of the field of view, 9 o'clock position. Then again at 12, 3, and 6 o'clock positions on the edge of the field of view, and the measurement process through the 2-inch, 50 millimeter depth is repeated. The range of sphere measurements positioned throughout the field of view gives us a good representation of the distortion of the lens within the cylinder of measurement in this test. The spreadsheet summarizes the test by showing telecentricity results at each location within the field of view in the columns of data, and distortion results in the rows of data. The combined data represents the level of performance of the snap optics. The snap is capable of providing machine spec or better results measuring the sphere throughout a cylinder approximately 3.3 inches, 83 millimeters in diameter, by 2 inches, 50 millimeters tall, without refocusing the optics or moving the stage. This demonstrated ability to take full advantage of the large field of view optics makes the snap a very fast and accurate measuring system.